Coming back to this session. This session is about face acquisition and analysis. We have 4 papers for this session. The first one is CS 3D LBP and geometry-based person-independent 3D facial action unit detection. So it's presented by Naslihan, Baya Mohun, Guin Zhang, and Matti Pätikkanen from Oulu University of Finland.
Thanks for the introduction. Good afternoon. We know that emotions are important. Understanding emotions plays a significant role in social communications and many professions, such as psychotherapy, education, law, and many others. But we computer scientists are also interested in understanding emotions. There is a big demand in human-computer interaction research to transfer emotions to computer-animated avatars and robots. It's also important to transmit explicit messages to computers by emotions. And face. Face is the key component in expressing our emotions, therefore, it is the key in understanding them. As we all know, facial expression analysis is studied extensively in literature. However, the majority of the previous work have focused generally on 2-dimensional data, images and videos. Because such data has a broad range of use, it's readily available, and because of the computational limitations in processing such data. However, capturing, processing, and storing 3-dimensional data increased rapidly during the last decade, and today such data is easily accessible and computational limitations are reduced. Therefore, in this work, we utilize 3-dimensional data for detecting facial action units. We have 2 proposals for that. We proposed a modified local binary patterns on the orientation of 3D face points, and secondly, we proposed a new set of person-independent geometric features. Now I want to emphasize benefits of employing 3D data in face analysis in general. First of all, its robust illumination changes. As we know, image-based face recognition is sensitive to shadows and illumination changes, but changes to illumination intensity or illumination direction does not affect 3-dimensional data acquisition. It can be acquired even in the dark. Secondly, 3D information could be used alone as a countermeasure for spoofing effects. It would be effective in 2D printed cases, and of course, it couldn't be a solution for 3D attacks. We should be aware of improving technologies such as face surgery or, to be more realistic, 3D printers. And lastly, in some cases, 3-dimensional information is enough to overcome challenges of background clutter. Shape and distance-based properties can be utilized for that purpose. In this example, subject can easily be segmented from the background using some planarity constraints. Now I want to talk a little bit on facial action coding system. Most automatic expression analysis studies focus on recognizing a small set of emotional expressions such as happiness, anger, surprise, disgust, sadness, and fear. However, the frequency of occurring such prototypic expressions in everyday life conditions are infrequent relative to other facial expressions. These prototypic expressions are exaggerated, and our expressions are often composed of few facial feature movements. To describe and measure these movements, Ekman and Friesen proposed an anatomically based system. They claim to describe all visually distinguishable facial activity on the basis of 44 unique action units. And the system also allows coding the intensity of action unit on a 5-point scale. Based on this system, facial expression may contain single action unit or combinations of several action units. Action units can be considered as a basis spanning the facial expression space by proper combinations. This example illustrates that surprise expression can be defined by a combination of 4 action units. Now, I want to present a video that displays some facial action units in a 3D face model. Some facial action units involve symmetrical motions. Some of them are asymmetric. And here we see combinations with associated with. As we see in this last frame, strong expressions are actually combined of several action units with different weights. Because of the reasons that I mentioned here, we could say that automatic facial action unit recognition is better suited to analyze facial expressions rather than recognizing basic 6 emotions. But due to subtle differences between certain action units, automatic facial action unit detection problem is relatively difficult. And now in this part of the presentation, I want to talk on previous studies. Existing approaches in 3-dimensional facial expression recognition research can be classified into 2 categories, feature-based and model-based. And majority of the works employ feature-based approaches. And among these feature-based methods, distance-based features and local structural features are popular ones. And among the works related to our structural feature-based proposal, we could mention Sandbach et al.'s study in detecting facial action units in 3D face data. Actually, we proposed a modification on that study. In that work, they applied traditional local binary patterns method to depth map images directly and also to the orientation of 3D face points. And I will explain orientation-based LBP in a few minutes. Sandbach and her colleagues later extended their work and transformed the 3D facial geometry into a 2D representation called azimuthal projection distance image, and they applied different binary patterns features to detect facial action units. We compare our work with this study and with the previous one. Now I want to explain the orientation-based local binary pattern descriptor. As you all might know, traditional LBP method utilizes an image point and its neighborhood. Pixel intensities of center point and neighboring points are compared and thresholded. This generates a binary descriptor for the center point, and this descriptor is shown to be quite successful in many computer vision applications, particularly in face analysis. Therefore, it's a good idea to adapt LBP to 3D domain. In order to adapt it, we need to define surfaces. A surface point can be characterized by its normal vector, that is its orientation, and its curvatures. These are local measures of a shape. A surface can have different amounts of curvatures in different directions, possibly with different signs, but orientation information can be used directly, and Sandbach et al. Proposed to use orientation information in calculating LBP descriptors on surfaces. In our work, we propose a slight modification on that approach and apply center-symmetric local binary patterns to describe surfaces locally. Center-symmetric local binary patterns is originally proposed to describe regions in images. And intensity values of opposing pixels are compared, and the differences are thresholded. It produces smaller number of LBP labels and results shorter histograms. Since the number of comparisons is halved here, it is also faster. We compare orientations in terms of angles between the opposing points to produce these labels, and angles are obtained by inner products. And the threshold function compares the angles with a threshold alpha. This is the first descriptor that we propose in this study, and now I want to explain our second descriptor based on geometric features. And among the works related to our geometry-based proposal, Soel and Demiral proposed measuring 5 facial distances, normalized with the width of the face. After 1 year, Tang and Huang proposed to use 24 distances and normalize them using neutral faces. Similarly, Srivastava and Rao used the geometrical displacement of a facial point from its position in a neutral face to that in the expressive face. And in these studies, distances are measured among facial landmarks, usually provided by the database owner, and these 3 works are meant for detecting basic 6 emotions. However, such distance-based approaches suffer from the diversity among different persons and different ages. Therefore, to overcome this challenge, neutral faces are employed. Neutral reference of each subject is used to specify the motion of a feature point or to normalize the feature. However, such solutions have some limitations. Neutral faces may not be available at all times, and even if it is available, one should annotate its content as neutral. In our study, instead of using distances directly or trying to normalize these distances using neutral faces, we propose using ratios on a single 3D face data. In this slide, we see action unit 12 right. It is lip right corner puller. Here, this specific action is expressed by different persons having different faces in shape and size. If we measure distances between particular facial landmarks, we would obtain different measurements for each person. The absolute distances, even for the same expression, yield differences, but we could see a similar harmony at all faces, and we tried to formulate this harmony. If we return back to the same example and examine the distance between right eye outer corner and lip right corner, and the distance between left eye outer corner and lip left corner, we could see that first one is always smaller than the second one for this specific action unit. Therefore, ratio of these distances is a significant person-independent feature to detect this specific action unit. We utilize ratios based on distances that are discriminative for one or multiple action units. If you look at, again, the first feature, it's also a significant one for the action unit 12 left, lip left corner puller. This feature takes 2 distinct values for these 2 expressions, and for other expressions, this ratio is always almost equal to 1. I will not go into details of other features, but similar to this one, we have features based on distances that are discriminative for some action units. We also utilized ratios of areas that exhibit strong changes in different expressions. In this slide, 2 area-based features and 2 exemplar expressions for each of them are shown. Here I select sample images in which the corresponding feature is significantly changing compared to other expressions. If you look at the first one, that ratio reflects the motion of the mouth along up and down direction. Similarly, the feature shown on the right describes lid motions, openness, or position. And finally, we utilized angles to describe the geometry of the expression face in a person-independent way. And in total, we defined 24 features, and we call them as ratio-based geometric features. And for the detection part, we employed random forest classifier. It is a collection of 3 predictors. It provides class posterior probabilities. Therefore, decision level combination of multiple detectors can easily be done. For each action unit, we evaluate both methods' individual performances and their combination. We use phosphorus database in our study. It contains 105 subjects with 29 professionals. Most of them are Caucasian, and they're expressing up to 24 action units. This database also provides facial landmarks. In addition to these landmarks, we manually marked eyes mid-points to describe upper facial action units better. And the results. This table shows our method's performances in the first 3 rows. That is center symmetric 3D LBP, ratio-based geometric features, and their combinations. And the table also shows performances reported in Sandbach et al.'s papers for comparison. I will talk on the average performances. When we look at the average performance of our center symmetric 3D LBP and traditional LBP descriptors, we can conclude that orientation-based 3D LBP descriptors can be implemented with shorter and faster way by utilizing center symmetric 3D LBP descriptor without degrading the performance. Secondly, our ratio-based geometric features. Its performance compares with the state-of-the-art methods. The construction of ratio-based geometric feature descriptor is simple, fast, and doesn't rely too much on the performance of pre-processing steps. In addition to that, we do not require neutral examples, and we could formulate the geometric rules for detection of action units on a single expression phase. And we believe that this method opens a promising direction for 2D facial action unit detection research. Finally, our combined descriptor. When we combine our geometry-based descriptor and center-symmetric 3D LBP method in the decision level, we obtain the highest detection performance for this database. Particularly, our combined method is better in detecting lower facial action units and shows comparable performance for the upper facial action units. And lastly, I want to talk on the limitations. Similar to other approaches that I mentioned here, our method is also based on facial landmarks. Fortunately, there exist a number of studies for automatic landmark detection for the 3D face data. Another limitation is the data itself. Because most 3D databases rely on laser scanners, therefore subjects are not in a natural environment. They are usually in a laboratory setting and sitting very still. Most probably, they have been told to pose in a certain way. That is why we obtain such high detection rates. And unfortunately, this is also true for 2D studies. However, I believe that we should be able to develop ways that could work in natural conditions. And I am aware that it is not an easy task to obtain such databases, and I want to thank for the database owners for their contributions in the field. And this slide concludes my presentation. Thank you very much for your attention.
The comment is that when the encoding of 3D data was integrated in the ISO IEC 19794-5, the face image encoding, there was also a standardized encoding of landmarks added to the standard. So for the 3D landmarks, maybe you want to consider those standardized codes just for clarity and avoiding misunderstandings. My question is regarding the action units. Is my understanding correct that an action unit is not the entire facial expression, but rather the muscle contraction at a given landmark, such that we had one slide where we have seen the overlay of multiple action units, that the activation at certain landmarks, the action of an action unit composes the expression. Is that correct? Or is an action unit just one expression?
Sometimes single action unit can be an expression itself. Sometimes combinations of them can be an expression.
Good. But the action unit as such is always a one-to-one relationship to one single landmark?
No, in my study, no, it's not. Actual ratios are dependent on action units, not the expressions, but the action units. Okay, ratios, not the facial landmarks. I just used landmarks for calculating these ratios.
Yes, it seems that your different ratios are computed using European distance. I would say maybe it's better to use geodesic distances. How do you think about it? Because it's
geometric or geodesic?
Geodesic distances.
Geodesic distances are not good in this case because they don't change in expression phase. The distances are same. Yes, they are same. you have deformable, we can discuss this later, but Euclidean distances changes, but geodesic distances remain same. We can discuss.
Okay, let's thank the speaker again. The second paper is by Raghavendra, Yang, Raja, and Bush from GUC Norway. It's about a new way of doing face recognition using light field camera. Okay, it's a special kind of camera, and it takes advantages of this special camera and to do face recognition.
So, thank you. So, good afternoon to all. So, myself, Raghavendra, I'm working in Norwegian Biometrics Laboratory, and this work has been collaborated with my colleagues, Björn, Kiran, and my supervisor, Christoph Busch. So, basic idea of this work is to investigate the newly available sensor, that is the light field camera, especially for the multiple face recognition at the various distance. So, to this extent, we try to investigate, and we also did some extensive experiments in comparison with the conventional 2D cameras, and we also present a couple of quantitative as well as in the qualitative results in order to bring out the merits and demerits of employing the same camera for the various biometric applications. So this is the outline of the whole presentation. So we start with the introduction for the light field cameras that will wrap up the basic information about the operation of these cameras and how exactly it is different from the conventional camera. And then we discuss the face recognition pipeline that can be built using the one commercially available camera, that is the light field camera, which is manufactured by the LETRO. And then we discussed our experimental results, the database collection, as well as the protocols that we employ doing our database. And finally, we have a lot of discussions that can bring out the merits and demerits of employing the same. So to start with, as we all know that the main intention of the light field camera is to capture all possible information that is available within the vicinity of the field of the view of the camera. That means that with the available, that means that, for example, if you consider in the conventional camera, the main intention of this conventional camera that it is always capture the intensity of in the light, and it will always discard the direction of the light. So in order to compensate for that one, so recently the light field camera has been investigated where the main idea is to record the intensity in addition to the direction. So as an advantage of this recording the direction, one can obtain not only the single image, but every possible image that can provide all possible information available within the field of the view. So in this case, we can offer a lot of flexibility as compared to that of a conventional camera. So this kind of camera will allow us to modify the image even after it is acquired. That means that we can change the view, we can change the focus, we can also increase the depth of view. So we will discuss all these features when we go in detail with this light field camera. So in order to make this light field camera realizable, so light field camera function is defined as the function of 7 different variables. So that is, the first two variables corresponds to the direction, that is measured in terms of azimuth as well as in the elevation. The third one is the wavelength that corresponds to in the color. The fourth one is in the time, and the last three corresponds to the 3 different dimensions. So what this equation essentially means is the all possible information one can visualize at each and every moment, at every position, and at every time. So basically, it will result in an holographic movie. So, but to realize this equation in the practical system, it requires a lot of computation. So, idea is to somehow we need to reduce the dimension which is used in this equation. To that extent, so they are going to reduce the 2 important parameters by assuming that image is acquired at only one moment, that is by discarding the color as well as in the time. So we now left with the dimension that can describe the direction as well as the 3 different planes. Next, in order to make it further computationally efficient, it is also assumed that all the incoming light rays to the camera is not occluded. So this assumption essentially means that once we know that the rays which are coming inside the camera is not blocked, it is quite easy for us to trace the rays which are entering the camera and identify the point where exactly it is interacting within the surface, obtain the position, corresponding to this position, obtain the angle. In this way, one can also study or one can also understand where actually these rays are originated and where they are ending up. So there are a couple of algorithms which will perform this. One of the famous algorithms is the ray tracing algorithm. So basically, main intention of this light field camera, we started from the 7-dimension and finally we reduced to the 4-dimension where we are interested in capturing only 2-dimension position and 2-dimension direction. So how to make this visible in terms of in the hardware? So this is how the hardware looks for the light field camera. There are 3 different well-established configurations. So the main idea is to introduce either a strip of in the micro lenses, or it may be in the pinhole array, or it may be in the mask. So idea of introducing this particular lenslet or the strip of the micro lenses is to divide all the incoming rays which is originating from the main lens in terms of in the angle, so that it will fall on the photosensor. So among these 3 different combinations that are available today, so the most widely used configuration is the micro lenses. In case of in the micro lens array, there are more than like 50,000 or 20,000 micro lenses which are of very small in size. These are placed before the sensor and next to the main lens, so that the main lens is always focused on the subject, and these micro lenses can be arranged in 2 different fashions. It can be arranged in the infinite focus, that is, all these micro lenses are focused on the main lens. Thus, from the perspective of in the micro lens, it will look like it is focused in the infinity. And in the second case, each of these micro lenses are focused at different focal length, so that we can extract the additional information. So this is the general setup which is used to capture the light field images. So once we capture the images, so that is all the light rays which will fall on the photosensor will result in a small, tiny, blurry images because of these small, tiny lenses. We then take 2 different steps to render the final image. For example, if you consider the plane u of v, this is the u of v and this is the s of t. So if we project all the rays from u of v to s of t, this is how these small, tiny images looks like. These are all blurry in nature, and these images corresponds to each of the micro lenses what we adopt here. Now to obtain the final image, we reproject this s of t back to the u of v. While doing this reprojection, it is quite simple. We just pick the first, for example, in order to reproject the first image, we take the first pixel value here, similarly in the second, similarly in the third, like that till all images to get the nice final image. So there are the 2 important observations one can make in this final rendered light field image. The first thing is the information in the vertical. For example, if you observe this particular image in the vertical direction, we can see that the information is available only up to the legs. But if you look into the last image here, the complete information about the statue is available. That is, it is providing a virtual parallel axis. In the similar way, one can also observe in the horizontal parallel axis. So for example, here in the first image, we can see the available information up to this edge, but here we can see the complete information here. So this is the main advantage of the light field camera, that can provide a complete information, and lot of sub-images are provided, so that the complete information about the subject or in the object can be easily obtained in a single shot, which was not available in any of this conventional camera. So these are the features of the light field camera that might be useful for the biometric analysis. The first thing is one can obtain a multiple focus image in a single shot. So the advantages is, for example, if you want to have a surveillance system in order to detect or in order to track a person at a distance, of course this kind of a camera is quite useful because we don't have a problem of the focus. And the second is there is no need to adjust a lens to set the focus. This is also a quite interesting property when we want to have in the surveillance at a distance, or we want to do in the surveillance of in the crowd behavior or something like that. So and the third important point is on the real-time exposure that can be achieved. And the last very important point is the size is very portable and the handheld, and hence it is more suitable for the biometric applications. And these are the 4 different advantages that are available with the light field camera as compared to that of a conventional one. The first thing is in the refocusing. Since we can have a multi-focus image, one can even try for in the refocusing, that is to focus the particular region of the interest in the obtained image. And the second one is all in focus. For example, if you want to increase the depth of field, simply we can combine the focused region in the multiple images and to obtain the all in focus image. And the third is the depth estimation. So in the single shot, we can estimate the depth and we can have a nice 3D image. And in the fourth one is in the synthetic aperture. So these are the 4 different features that will in compared to in the conventional camera that will look as an advantage. So in the market, there are 2 different cameras available. The first one is the recently released in the last year from the Letro, which is the first consumable camera. So this is of about 11 megares. The specification what they use to describe here is the resolution. Here is the megares, but it can render only 1.2 megapixel of the spatial resolution. And it is having more than 100,000 micro lenses, which are focused at an infinity. And the main lens is at the fixed focus of f/4. And finally, it is of low cost, and it costs you around $300, and it is of very user-friendly. And the second available device is from the Retrix. It is the first industrial model which has been released in 2011. And this model are quite flexible. That means that we can also change the optics available here according to our application. And it is also of in the same resolution of 11 megares, but it is going to render like 2.7 megapixel of spatial resolution. So it is having more spatial resolution just because it is using the less micro lenses, and thus each micro lenses will occupy more space in the sensor, and that is the reason why it is having more resolution. So and each of these lenses are focused differently. As a result, it will result in the more computation. In addition to frames, it can also capture the video at the rate of 6 frames. But this camera is high in the cost. That means that it will cost you around $7,000 for the basic model. So by comparing these 2 cameras, we just pick the first one from the Letro, which is very low cost and which is user friendly and also less computational compared to in the other one, and also it is more flexible. So now we try to build in the new database based on the camera what we selected. So in order to have the comprehensive comparison, we try to compare the data. We try to compare the performance of the light field camera with the conventional camera. To this extent, we choose the conventional camera as in the Sony DSC-S750. These are all the parameters that are technical parameters associated with both Letro as well as in the conventional camera. So among these parameters, the most interesting parameter is about the resolution. The resolution of the conventional one is about 7.2 megapixel, whereas for in the Letro is just 1.2 megapixel. And the second important observation is about the focal length, which is quite more in case of in the Letro. And the third is about the aperture range, which is more or less the constant because we can obtain the synthetic aperture with light field cameras. So with this setup, we construct a new database. To this extent, we employed the 25 subjects, out of which 23 are male and 2 are the females. And we designed 3 scenarios. So one corresponds to in the indoor, and other corresponds to in the corridor, other corresponds to in the outdoor. In case of in the indoor scenario, we don't have any sunlight. It is completely a closed scenario. Where in case of in the second scenario, we have both sunlight as well as in the artificial light. Where in the third one, we have completely an outdoor scenario with the varying sunlight. So next, for the enrollment, we used entirely a different camera because our idea is to construct this database by looking into typical applications like in the border control or in the access control, where we have an enrolled sample in the good quality conditions. So in order to simulate that particular task, we try to come up with the enrollment sample acquired in a completely controlled scenario using a DSLR camera of Canon EOS. And for the probe sample, we used both light field as well as in the conventional camera, and we collected 141 probe samples, which are distributed in all the 3 scenarios. So this is the typical setup what we did for the enrollment data collection. So we have a nice studio environment in the lab, and we have the diffusers, and we also have in the camera mounted about 2.5 meters away from in the chair. So we try to follow all ISO standards, especially for the passport, to try to simulate the similar situation. And here we captured 8 samples for each user, thereby simulating the different poses here. And the first one is the neutral, and second one is the smile, and the rest 6 will represent the different poses. And for the probe data collection, since we are interested in identifying more than one person at a time, so we try to have in each probe sample will be having more than 2 between 2 to 4 subjects. And each of these subjects are scattered between a distance of 0.5 meters to 20 meters. Thereby we can investigate the performance of light field camera even with the distance. And while data capturing conditions, we don't have any additional restrictions. We allowed variable poses, we allowed variable expression, and also variable light conditions. And with this, we collected about 445 subjects. Even though we have 141 probe samples, since each probe sample can have more than one subject at a time, so finally it resulted in 445 subjects out of 141 probe samples, and these are distributed in all the 3 conditions. Well, this is how the image from the light field camera will appear. So in the single shot, we can obtain the multiple focus image or multiple depth images. And what we can observe here is, if you can see the figure A, the focus is well set towards the back end. As it proceeds towards the figure D, the focus is set in the front end as compared to that of in the back. So this is the additional advantage of employing a light field camera as compared to a conventional one. So these are the example of the probe samples what we acquired. For the simplicity, I just included one focus image or one depth image from the light field camera. So these are the samples collected using in the conventional camera. So these are the different scenarios. And in order to make this database more challenging with respect to the pose and also towards in the illumination, we just allowed variable poses and also a kind of expressions. And this is the identification flow work we propose for a light field camera. So starting within the light field acquisition, we get in multiple depth images. On each depth image, we run a phase detector. The phase detector employed in this work is been built using in the OpenCV implementation, which is available openly. And then once we obtain this phase detection result, then we propose a new scheme for selecting in the best focus image on which we can run in feature extraction and identification. So here is in the illustration of in the first step. So with respect to the different depth images, we run the phase detector to obtain the phase region. So this is the results what we obtained from in the phase detector. So in order to make the system more robust, what we try to do here is we select the result of the phase detector that detected the large number of phases. And then we use that as in the ground truth, and we extract the phases from all the depth image. So for instance, this is the depth image what we can obtain for in the single subject. For in the single subject, in the next step, we try to select the best focus image from these depth images. To this extent, we propose a scheme on the wavelength energy-based technique. We have 3 good reasons why we are using this. The first thing is what we can observe from these quantitative values is this measure is monotonic. That means that if the focus is very nice, it will give the largest value. As the focus goes down, it will give the lowest value. And the second thing is it is robust to noise. And the third important observation is it is independent of in the structure. So based on this measure, we will just choose the first image that corresponds to in the largest energy that always corresponds to the best focus image. Then in order to carry out the identification on this selected image, we employed the 2 different feature extraction techniques that are available openly, and 2 different classifiers. So depending on using 2 feature extraction and 2 different classifiers, we built 4 different algorithms by combining them. And then for the experimental protocol, we use the enrollment training samples as in the enrollment samples that are obtained in the control condition. As in the probe, we have 141 probe sample collected using both light field as well as in the conventional camera. In order to train the KDA subspace, we just use the polynomial kernel with degree 2. These values are selected experimentally. And then for the subspace training, we used 1600 samples from the FRGC phase database. And for the sparse representation, we use the open source of SPG L1 solver, which is based on the spectral estimation. Well, this is the first result compared to in the conventional as well as in the light field camera. This is the result of the phase detection. So here we can observe that there is a great improvement of about 7% as compared to in the light field camera. In order to see why it is so here is in the qualitative results. So for the conventional camera, here is the phase detection result what we can obtain, because since the conventional camera can set a focus at only one region, obviously it is missing out a lot of information which are presented in the other focus region. But in case of in the light field camera, this is not the case. So we can easily detect all the phases which are spread from 0.5 meters to 20 meters irrespective of the scenarios. Well, we then carried out further identification results on all the 4 algorithms what we did here. So as we can observe here, the conventional camera, the best result from the conventional camera is noted for 53%, where in case of in the light field it is 61%, and still there is a gain of about 8% using the available scheme. So since we have 4 algorithms, we thought of doing in the fusion. So this is a multi-algorithm fusion. The fusion is carried out at in the decision level using in the OR rule. So first we start within the 2 fusion algorithm. So we have like 6 different combinations. Here also it can be observed that the performance of the conventional camera is much better than the light field camera. And in case of in the next 3 algorithm fusion, here also the similar situation can be observed. At least the 4% of gain is noticed. And finally, in the all fusion case, so we can finally conclude here by looking into these values is about 75% we can achieve with the conventional, whereas the light field camera can go up to 79%. So roughly we can achieve about 4% of gain by employing the light field camera. So what are the observations? So these are the basic observations what we obtained when we try to experiment this light field camera for this. So the main advantage of using the light field camera is that it can provide a multiple focus image in a single shot. As an advantage, one can obtain a nice 3D reconstruction. One can also try and fusion of in the in-complement scheme, because the multifocus image will always have supplement information between them. And we can also try to work out the try to overcome the occluded information, for example, by exploiting the parallax information that is also available within the light field camera. And then we found that it is more suitable, especially for the wide area surveillance, and more precisely for the face recognition at a distance, as well as in the face recognition in the crowd. And the last but not least, the low cost as well as the small size will also motivate us to employ and deploy this kind of cameras, which are much more advantageous as compared to that of in the conventional camera. So thank you. So if you have some questions, I'm happy to talk.
Questions?
You were emphasizing that the camera is low cost. Can you compare it with a traditional 2D camera?
So because the camera what we employed is the Sony one, the Sony DS, it is a normal digital camera, the low-end digital camera, it cost you around $250. The what we spent for the light field camera is $300. So that is quite flexible.
You said that using this sort of camera, you can change the angle of view after capturing the image. I was wondering what sort of format the image will be, and what's the size of the acquired image.
Yeah, so basically the letter outputs a file in the raw format. They have their own specific format called .lfc. So we wrote in the code to attack that file. That means that to understand that file and capture all the information. So basically the size of .lfc file will be in the range of about 30 KB, and the number of depth images will also varies accordingly. So we can have a function to set the number of depth images. But it is not like in the conventional camera. You click, you get a photo. It's not like that. So you need to write your own code to access those data and the meta information. Then you need to use the meta information to construct these kind of depth images.
Okay. No more questions. Then let's thank the speaker again.
Thank you.
The third paper is presented by Jago and others from several institutes. One is from Brazil, another is from India. It's about a question regarding how face excluding can be used, and the proposed method.
Okay, good afternoon everyone. My name is Thiago, and here to present the work Can Face Anti-Spoofing Countermeasures work in a real-world scenario. Here are the topics that I will present today. First, I will talk about the spoofing in face recognition. Second, I will talk about the resources that we studied here. After that, I will talk about the experiments and the results, trying to answer the main question. And finally, the conclusions and the future work. So, spoofing in face biometrics. So what is spoofing in biometrics? An spoofing attack consists of a direct attack to the biometric sensor. In this example, we have Mr. Simpson pretending to be Mr. Burns in order to have access on a high security room in a nuclear facility using his photograph, and he succeeded. They are efficient and robust to the face recognition system in wide use in the market, and most of it have this kind of issue. So how did Mr. Simpson got a picture from Mr. Burns? It turns out there's a lot of multimedia data available on the web, so it's not that hard to get a picture from anyone else. You can spoof a face recognition system using photographs, as Homer did, videos, and also masks. It is possible also to use makeup or even a plastic surgery, but photographs and videos can be considered more common. So we need countermeasures to make a face recognition system more secure in this point of view. Today the countermeasures are focusing to perform well in databases, but what can we say about the generalization of these countermeasures in a more heterogeneous test? So the motivation of this work is to analyze if the countermeasures in the literature can work in a more realistic condition. So let's do the studied resources here. So there are some works in the literature addressing the face anti-spoofing. So what we did, we took 3 freely available countermeasures and 2 freely available video with face anti-spoofing and databases, and we applied some evaluation protocols in order to evaluate the main question. It's important to remark here with the countermeasures and the video databases are relevant with respect to the state of the art in this research. The first countermeasure studied here is the motion correlation proposed by Angels et al. In 2011. This countermeasure measures the motion correlation between the facial region and its background. The second countermeasure is textures with LBP, proposed by Mata et al. And Chingovska in 2011 and 2012, respectively. The attack media has different texture patterns compared with real faces. As someone of you observed in the spoofing session, there was some attacks with the printed paper, which is, the paper has a different texture pattern compared with the real faces, so LBP tries to deal with it. Finally, the third countermeasure is dynamic texture with LBP top, proposed by Freitas Pereira et al. And Comulaine in 2012. LBP top is acronym to local binary patterns from 3 orthogonal planes. Texture and motion patterns are 2 important cues to detect face spoof, and LBP top deal with both cues. Let's talk about the databases. The first database evaluated here was the replay attack databases, which contain video files of real access and attacks of 50 identities. This database has different kinds of attacks, different conditions and support conditions, and it's freely available from the load from here. The second database is the Keisha face anti-spoofing databases, which contain also video files of real access and attacks of 50 identities. This database has different kinds of attacks and different levels of media quality, and also can be downloaded from here. The experiments and the results that we got here. We talk about the protocols that we use in this work. The first one is the intra-test protocol. The goal of this protocol is to evaluate how each countermeasure perform in each database. So you train a countermeasure with the replay attack database, calibrate it, and test it in the replay attack database. And do the same with the cache offense anti-spoofing databases. There's nothing new here. It's basically the protocol that the databases provide. The second protocol called intertest. This protocol tries to emulate a more heterogeneous condition. So you train a countermeasure here, let's say the motion correlation, calibrate it, and test it with the cache offense anti-spoofing database. And vice versa. You train and tune a countermeasure with the cache offense anti-spoofing database and test it with the replay attack database. Here is some results. So here we have the countermeasures, motion, correlation, LBP, and LBP top. Working in the replay attack in the case of anti-spoofing database. As a performance measure here, we use the half total error rate. So what can be observed here? The countermeasures and has different performances with different databases. So, but one important thing here is about the countermeasure seems to give a good generalization capability. If you observe the performance in the development set that we use to tune the countermeasures, they are quite similar to we got in the test set of the databases, except for this one. Now the results using the intertest protocol. So we have here the countermeasures, train and then tune with one database and test with the test set with another one. So the same performance measure, the performance in the development set and the performance in the test set. So the countermeasures do not generalize as expected. Why? The database has some differences. They have different kind of attacks and have different ways to perform an attack. It seems the countermeasure are not that robust to be applied in a word scenario. So we need something more robust. So then there's a lot of bias here. So the countermeasures are biased in the databases. An intuitive approach to deal with this is to combine both databases. So you train a countermeasure with a combination of both databases and report the results using the test set of each database, replay and the cache. From the results here, each countermeasure, motion, LBP and LBP top, tested with the replay and the cache. Sorry. And you have different the performances here in each database. So there is a strong bias to the replay attack database. The countermeasures are biasing to one specific database. Additionally, this technique has one disadvantage. When you try to, for example, add more attacks or a different database in this scheme, you have to train all the countermeasure again, which may be unpleasant. Another approach to deal with this different kind of attacks is called the score level fusion-based framework. So in this framework, you train and tune a countermeasure with one database and train the same countermeasure, another machine, with another database. So each one has a score and you fuse these scores. In this work, we organized this framework, training each the same countermeasure with different databases, but we can make any combination that you want. For example, we can train specific countermeasures to solve any specific kind of attack. For example, we can build a countermeasure specific to print attacks or another one specific to video attacks, and we can combine it. And also we can combine countermeasures that are complementary, not just with respect with data. Before to go to the result analysis, a piece of word about the combination of different classifiers. Sometimes when you fuse different classifiers, you got a worse result. So Kulcheva et al. Studied different strategies to measure the quality of combining classifiers. And they suggested to use the Q statistic. The Q statistic is basically a quantitative measure that measures the level of dependence of classifiers. So this measure, the range of these measures goes to -1 to 1. So what is important here to interpret? When you have Q close to 1, the classifiers are good for fusion, close to 0, sorry. Close to 0, the classifiers are good for fusion, so a fusion will be a good business. When you have Q close to 1, the countermeasures, the classifiers are quite similar, and probably no improvement will be get with the fusion. When you have Q close to -1, the countermeasures, the classifiers oppose each other, and high degradation will be get when you fuse the classifiers. So the results using the scar level fusion basic framework. So we have here the countermeasures, motion, LBP, and LBP top, tested with the replay and Keisha. We have here the performance, for example, for the motion correlation. This performance in the test set of each database are quite close to the performance that we got using the intra-test protocol. So we were able to create a framework that was able to get almost the same performance that we got with training and testing with one database. And the Q here is close to 0. So analyzing before the effectiveness of the fusion was close to 0, so will be a good business, and it was. It was not the same for the LBP and the LBP top. So the motion correlation here is more suitable using this framework. So we can use the motion correlation to create a framework that was able to classify the both databases. Some conclusions and the future work. Countermeasures and databases proposed in the literature have low generalization power in more heterogeneous tests, which suggests that the answer for this question is no. We cannot use these countermeasures in a real-world scenario. So 2 approaches to deal with multiple databases were present here: the combination of multiple databases and the scar-level fusion-based framework. The scar-level fusion-based framework is an easy and effective way to combine different countermeasures here. So we can, as we did here, combine different databases, but we can combine, for example, different kinds of attacks or countermeasures that are complementary. We need more databases in order to validate the framework. Database that has more challenging attacks and tested with different countermeasures. Also, for the future work, we need to try different fusion strategies in order to improve the results of this framework. This research is reproducible. You can download the source code from here. And this research was developed with the free signal processing and the machine learned Bob, which can also be freely downloaded from here. Thanks for your attention.
If I understand you well, you use the 2 databases to come up with this score fusion file. What do you think the program is still there? Say, for example, if tomorrow you
yeah, we need more database in that sense. That's the only two databases available. So we can consider that this framework, the fusion, for example, for these two different databases, that they have different kind of attacks. So at least you have more attacks in learned in your framework. If you have a new database with more well-thinking attacks, probably will fail. But you have attacks that was already thinking, probably will be worse. So it's like an antivirus. You always have to update.
Yes.
Do you have an opinion on why the experiment was biased to the nuclear database and not the KCO database? Why?
The database has some difference here. So, for example, the attacks in the replay attack database were so close up from here, and the cache is from here. The cache has, for example, some warped attacks. The database has difference, and the countermeasures are well fitted in this data.
I have a question. I believe you attempted to test the spoofing anti-spoofing systems in the past few days.
Yeah.
How have you been successful in spoofing those systems?
I was able to spoof, but I have to admit it was not that easy. It was not that easy. Or for example, if you have a low quality phone that was mine, I was not able to spoof. But if you try hard, you can spoof. I was able to spoof the system.
You were able to do.
Yes, at least the face recognition. Not for example, the near infrared was not able to spoof.
Okay, there will be a best spoofer award on yeah, let's see who's that. Okay, thank you again. Our last paper is one from Tsinghua University, presented by Jia, Fan, and Wang, and Professor Ding. It's about generating multiple illumination space images from a single image.
This one. Okay, this one. Okay, I'm very honored to be here to show you some of our research. Wow. I'm Jia Qiang from Tsinghua University in China, Beijing. And my speech will be split into these parts, the introduction and our general idea, and the algorithm. I split the algorithm into two parts, and the experiments and the conclusion and our future work. The illumination problem is a very serious problem in face recognition because it could cause great changes within one subject, and so it will degrade the performance of the system. And on the other side, the illumination problem is very hard to solve. If we look at the Lambertian reflectance model, the illumination, the face image is influenced by a lot of factors, such as the reflectance, the normal vector, and the illumination. So it is actually a U-post problem. And to solve this problem, we should put more knowledge in it. The existing illumination algorithm could be categorized into two groups. The first is the pre-processing method. they add the pre-processing procedure before the feature extraction to normalize the illumination. And most of the pre-processing methods are without bootstraps, such as Retinex, SQI, LTV, DCT, LWT, and so on. And these methods, the advantage of these methods are they are very simple. They have very low complexity. But on the other side, they have their limitations. They can, what they try to solve is not aimed at the faces. In other words, if the picture is not human face, it's just a mountain, a Siri, or other things, it can also do the normalization. So their effect, they are less effective, I suppose. Compared with the second category, which is the face relighting, I suppose that the pre-processing has lost some informations. So the second group is face relighting. These algorithms try to generate more illuminations of the gallery set, so it can depict the illuminations of space. But the disadvantage of the existing relighting method is that for those methods that with single sample input as input, they usually require 3D models. Not usually, they always require 3D models or estimating 3D models. So that would bring them inaccuracy, such as the morphable face. Then for those methods that don't need the 3D models, they must require the multi-sample as input. So that will limit their application, such as the illumination cone method. So what do we want is we use single sample as input, as well at the same time we can get rid of the 3D model. We want them both. But how can achieve that? In order to solve the ill-posed problem, we have to put some knowledge into our algorithm. And what kind of face knowledge? We could see that the 3D model and the multiple input is the description of the human face. So they are the face knowledge. And on the other side, the face databases, it has a lot of subjects and a lot of illuminations, so it could also be regarded as the face knowledge. Can we use the face database to substitute the 3D model and the multiple input? So our work or our goal is to design a face relighting algorithm which relies only on multi-illumination face databases and with only one single sample as input and get rid of the 3D model. Just like this. To solve this problem, we use the linear Lambertian property to generate new ID from the ID in the databases. Here we must make it clear that the new ID and the given ID, their illumination should be the same. And if we look at the Lambertian reflectance model, it could tell us that the linear coefficients of the representation won't change while the illumination changes. And how to get the linear coefficient? We must limit the input template. The illumination of the template should be front lighted, and the databases, there should be a group of pictures which is also front lighted. And if we have got the after we got the coefficients, we could apply the coefficients into the different groups of our databases, the different illumination group of our databases, so that we can generate different illuminations. So our algorithm, a first part of our algorithm is like this. We should use in face databases as our bootstrap. That contains multiple subjects and multiple specific illuminations. I mean specific is the illuminations won't change across the subject. We selected the multiply databases as our bootstrap. It contains 249 subjects and 2 expressions for each subject and 20 illuminations for each expression, just like the picture shows. So we could say that there were 20 illumination group in our bootstrap, and there are 20 illumination group in our bootstrap, and we can generate 20 images with one input. And we got the bootstrap, and we could use the bootstrap to linear express the template. And after we got the linear expression coefficients, we could apply the coefficients to the 20 groups and generate 20 images. That formula shows why the coefficient won't change across illuminations. And that is the structure of our initial generation. We call it initial generation. The first step is to calculate the coefficient, use the template and the front-lighted pictures in our database. And the second is to apply the coefficients into the database, the 20 groups, to generate 20 images. And there are some problems in our initial generation results. We could see from the example. From the image domain, we can see that the generated results has some false structures, such as fake glasses and multi-draws. And we could see from the picture E that some facial details has disappeared. From the DCT domain, we could see that a high frequency coefficients has been distorted. So we could say that there exists great inaccuracy in small-scale information in the detail generation, in the initial generation results. So how to solve this problem? We could see that the small-scale information is inaccurate, but the large-scale information of our initial generation is correct. So we could use a Gaussian filter to get the large-scale information, and we use according to the Lambo reflection model, we could use the assumption that L light changes slowly while the R changes sharply to split the small scale information from the template IF to get the R. And at the last step, we combine the large scale information and the small scale information and got the final result, the IK. This is the whole structure of our algorithm. We do the initial generation first, and we filter the result and get LK, and we extract the small scale information from the template, and finally we synthesize the LK and R to get the IK. And this is the process of our algorithm and the result. We could see from the process that we could see from the line we could see from the line F that the final result is more, has more details and more identification information than the line D. And the generated illumination is more realistic. You could see the shadows beside the nose. And we conduct experiments both on the extended ELB and the FRGC 2.0. These two databases are different. They are both real illuminations, but the extended ELB is more in the laboratory, is more simple, and the FRGC is, the illumination of FRGC is more complicated. And the number of the subjects and the enrolled images and test images are shown in the slides, and we use the average template to enroll, and we train the PCE and LDA parameter with the gallery set. And the results shows that we compared our method with the pre-processing method. The result shows that our generative method has outperformed all the pre-processing methods, such as Retinux and SQI or LTV. And for the second one, our method could be implemented altogether with the pre-processing method and get a more good result, a better result. And the experiment on FRGC also shows the same result. That is, the generative method outperforms the pre-processing method. So to conclude, to sum up, our method has these advantages. First, our generated illumination contains the face knowledge, such as shadow or something. That is because the knowledge has been contained in our databases, our bootstraps. And second, we only need a single sample. Third, we don't need the 3D model. And fourth, we don't need to alignment the feature points. So our algorithm has low complexity. And fifth, our algorithm is more flexible to use because we generate a lot of illuminations, a lot of images, so that the face recognition system can use more information, such as the mean, both the mean and the variance, and so on. And the future work, and I also want to mention the future work and the limitations of our method. The first one, the most important one, is this generative method is greatly limited by the bootstrap. There are two aspects. First is the quantity of the subjects of the bootstrap. The more, the better. Second is a variety of illuminations. We could see from the FRGC results, the result is not as good as those from the ELB. That is because the FRGC's illumination is more complicated, and that is not the same with the bootstrap we used, which is multiply. So if we have more illuminations in the bootstrap, we could solve this problem. We could get better results. Oh, sorry. And the second one is our generated illumination doesn't contain the detail of the illumination. We have conduct conduct the experiment that we use one of the bootstrap as template, one subject of the bootstrap as template, and the others as the new bootstrap. And we generated the images, it's like the third one. Compared with the real image, which is the middle one, we could see that the edge of the shadow is not very clear. That is because we have done the Gaussian filter during the process. So it has filtered the light, filtered the illumination, so that it won't contain any more edge of any more detail of the illumination. That is hard to solve, which is our limitation. And the third one, the assumption that the L changes relatively slow, which is not always true, but it won't be a very big, very serious problem in our algorithm. Why? Because our template is often front lighted. In the front lighted image, there was no shadow. No shadow, which means the illumination changes slowly. There was that doesn't like the one with the heavy shadows. In the shadows edge, the light changes very sharply, which is not, which will not happen in our case. So that is all of my speech. Thank you very much. You could see that my English is not very good, so if you ask questions, I make it more slow so I could understand what you mean. Thank you.
Okay, let me ask you a question first.
Okay.
Have you tested your algorithm derived from the Pi database to some other type of images? Like
You mean I change my bootstrap to other databases?
Yeah.
I haven't found the other databases are not as good as MultiPy to be as a bootstrap, because that won't contain so many subjects and so many illuminations at the same time. These illuminations in my bootstrap must be specific. Which means the illuminations across the subjects should be the same. You could see that. We could see that from the. We could see that from this picture. For different subjects, the illumination should be the same.
Yeah.
So we can't find any better.
I'm fine. Just to illuminate another subject in some other databases in the same way as the Pi database illuminating.
Oh yes. What we have done is to illuminate, to generate the illumination just like the MultiPy.
Yeah, just now. Can you generate your algorithm derived from MultiPy to some other phases like Chinese passport photo from lighting? Can you?
Yes, of course. We do generation. We could generate the faces of a new ID, any ID, any new ID, any new face, because we use the linear Lambertian property that to linear represent the new face with the bootstrap.
It will be good if you add some such examples into the paper.
The example I've gave is not in the MultiPy database.
Okay.
This is in the FRGC database.
Very nice paper, thank you. Just
You're
one
welcome.
question, how does it behave in case of saturation? If the original image is saturated or spectralities that brings non-linearity in the model? Any results on that?
Excuse me, you mean the original image is what?
Saturated.
Saturated.
Yeah,
Oh,
saturated.
I mean, no, no. You know, a lot of images in the FRGC is saturated, and the experiment results in FRGC is not very good. I think it's possibly because the illumination in multiply is very different from the illumination in FRGC. So if we could find more a better bootstrap that contains a lot of subjects, but both in the same illumination, we could do that experiment. It is not limited, so we can know whether it can be good.
Thank you.
I would like to ask another question. You showed that there may be some artifacts. Okay, your algorithm has an advantage of not needing some alignment.
Yeah.
Assuming you have some landmark alignment to do the normalization, or would it overcome that kind of problem?
Why we don't need the alignment of feature point is that we believe that the different kind of human faces are included in our bootstrap. So
Okay, you are assuming it's included, all the shapes kind of thing.
yeah, yes, included in the bootstrap. So we can adjust the coefficient of the linear representation to solve that problem. If that face is not like what the template, the coefficient will be very small. And if that is exactly like the template, this coefficient of this face will be strong. And
Okay, thank you.